Not today.
Here is the internet in this computer, and I can connect your computer.
No, not like to that mainframe. We get.
As for now, I get the file here.
Oh, okay.
Yes.
We'll work on it later, because I was thinking of kind of going along with what we're doing, and I was thinking of something that would be different. Have you done any assembler?
Myself, yeah.
Oh, no, not you.
Yeah, they didn't have yet, and it's, I have told that it's the problem. We just have too few time to squeeze assembler in, but I have great plans.
Would you try that? I could try a real simple program.
It would be good, because I haven't yet tried, and it is important for them, so.
Oh, good, okay. So that's right. That way it'll give them some hands-on along with theory.
Yeah. Okay. It's rather good, because assembly is important, and it's always.
Yes, assembly. When we will learn assembly?
And I work on such access to the mainframe. Our course. I hope in 2 days I would know definitely if we have it or we have not.
Good, okay, good.
So the translation is going.
Oh, very good. Is that me? It's a little bit of a delay.
Юра, ви інтерактивну трансляцію почнете, правда?
Та зараз я знайду людей, які будуть.
Бо це запис.
А минулої лекції нема запису?
На жаль, ні. Я тоді запізно, але теж Джим робив по своїх слайдах, чи Джим обіцяв їх викликати?
Так, він їх виклав.
А, викликав, я ж.
Hi, how you doing?
Що робиш? Якщо щось питайтеся, питайтеся в Джима, питайтеся в мене.
Ти на цьому курсі, як я минулого року.
I'm going to redo this Life of an I.O. Yeah, I don't think anybody was attending last time. Well, first I'll give the quiz, and everybody could be thinking about the quiz question, how to answer it during the discussion. Uh-oh. Oh my goodness, let's see.
The biggest problem.
Is one of these things a word wrap? Okay.
It's the problem of.
Oh, I'll figure this out. Well, go do your meeting. I'll figure this out with these guys. They're like wizards.
No, I see. Is this guy?
Yeah.
Will I have a camera or?
Склероз. I'm deeply sorry.
Very good.
Напишіть мені в Slack. Я... Maybe I will analyze it a little bit. And something like
Very good. Yeah. Be good enough for me to talk.
видно.
Так.
Я бачу, ви вже.
Але треба дослідити.
Ні,
Ні, то нормально.
Young guys, they can see like clocks.
Actually not.
Now they are 4, you know, it's like big improvement.
3 minutes. Anybody else online?
As it is. Спасибо. Окей. Як ти минулого разу робив?
Я буду наверху, я ж запитаю, може нас тут є камера. Чи я
О!
не відправлять?
Здається, в мене склероз, я трохи не запустив.
Зараз. I for the second time forgot to take the camera for you.
Oh.
I will handle it somehow. Там про питання.
Just in case.
Что? Я не
Oh,
чую.
I forgot, I have a bunch of
Володя,
them.
прошу.
А, хорошо.
Here, I got my own, you can keep these. That way you can keep these in your, little one file in my curial, case.
They're all different types?
Ah, no, most of them are black, they got blue. What else is nice?
Вже все окей, так?
Так, Роман є. Боже, лучше просто. Розказуй.
Я ще вас запитаюся, може ви хтось глибше заходив в цей курс? Є там рано чи пізно доступ до реального заліза?
Так, там завдання є.
А, там є завдання. Як їх виглядає?
Програмування саме є. Ну, то вам видають пам'ятники, якби їхні термінали, ти там код пишеш.
О. А де вони всі просто в таких модулях воно є?
Починаючи з 4-го, здається.
Модулі чи курс?
Так. Ну, то вже якщо у нас третя лекція, то у нас на наступну лекцію вже буде.
Так.
Jim, students tell me that there is access to IBM mainframe terminal in this course.
Oh, there is?
They were most throughout the miss, so that they already...
Next time we'll be doing, some coding and we're actually working with the machine.
Це такий доступ до їхнього комп'ютера, це якби, ну, можна сказати, емулятор в браузері.
Віртуально.
Ну,
Так.
киньте мені до цієї, а там подивимося.
Я думаю, там є.
Ні, ми це у нас будуть модуля, де воно трапиться, щоб я не різкав, то я визвучив.
That they all can log on independently.
I'm not sure, I need to check with myself,
Okay.
but
Okay.
at last it's some, as guys think it's maybe some kind of emulation, but it's terminal.
If it's with IBM, they're probably giving them access to a VM.
I hope so, yes.
Over VM, I'm almost positive.
And it's not a problem for them to
Yeah.
start small VM and
IBM does make a machine that sort of emulates it. Oh, I forgot the name of it, but it's like
Another acronym?
it's like a mainframe on a PC. Yeah. Okay. So start?
Yes.
Okay, hey, welcome back. So what we're going to do is talk about I/O again. This will be last time, and we'll get into programming or something useful like that. I/O is important because as usually entry-level people, the first jobs you get will be some like programmer, administrator, and the first jobs you get, or the tasks you get, have to do with input-output. So understanding disk, how efficiencies work, effectiveness of disk drives, how to get data back and forth is an important skill. Today what we're going to do is, it usually works backwards. Usually you get the lecture, then you get the question. So I'm going to give you the question,
And then
get the lecture, and then you guys can either give me an answer right away or think about it and give me an answer next time or right now. Good? So here's the question. The situation is this. Your role, you're a newly hired programmer analyst. That means you understand the user's business and you understand programming and certainly I/O by the end of this discussion. You report to, the lady who hired you is June Johnson, and she's the manager, she works for IT, and she's the manager of the personnel system. So that would be recording things about people, payrolls, things like that. So lots of data. Because they have data on all these employees of a large company. So you get hired, Now, this typically happens. Ms. Johnson, excuse me, she sort of acts as the IT person to the director of human resources. So he's the user. He's got lots of people working for him. He takes care of payroll, personnel, insurance for the employees, all kinds of things like that. So he needs the support of IT. In a big company, the departments have to pay for the IT services. So weekly, typically, Jane and Ralph get together, they talk about how's our projects, how's IT doing. Ralph tells Jane, I'm paying too much. But that's a story everybody has. You go to the store, food costs too much, petrol costs too much, everything costs too much. So that's what she hears every week from Ralph. It's too expensive, I want to pay less for IT. But this time she has an answer. She hired one of you. And you came in saying, look, I had this extra class over summer. I'm a wizard at I/O. You got an I/O problem, I'll have a solution. So, Jane tells Ralph this, and she says, look, why don't you give me about 40 hours to employ this new person, and we'll try this project. And it'll take about 40 hours, and it'll take a duration time about 2 weeks. So, Jane recommends the study on doing something probably with I/O, because she has a feeling like that's where money can be saved, usually the case. So, here's what you did. You notice that one of the recurring tasks that you have to do over and over is backing up the personnel system from disk, of course it's on, to another set of disk drives. Backup is important. And you do that every night. And you notice it takes a lot of I/O and consequently a lot of computer cycles. So the computers is what's getting paid for by Ralph. So here's what you do. You go, I know, I took this class, and what they showed me is I/O is very costly from the computer utilization standpoint. It's not only the disk drives that are being used a lot, but it takes a lot of computer CPU resources to create that I/O and get it going. If I can reduce the number of I/Os, I'll look like a hero and keep my job. So, how are we gonna reduce I/O?
Okay, we can when we take the data to save it into DSD, we had it in the buffer.
Yeah.
And then we can, when we give it to the main DSD, in the same time we can give it to the backup DSD.
Right. How many I/Os are being performed? It's a function of how many bytes of data you get each time.
Yes, and if we get on the night backup, we get it one time from the data, and then we take it from the DSD and to the backup server. And in this way, we took it one time and send it 2 times. A little improvement.
Yes. So what we can do is reduce the number of I/Os. The way that can be done is do more every I/O. So just increase the number of records that are transferred on each I/O. You do that by increasing the buffers. All this will be talked about. So if we could increase the buffer size, every I/O will transfer more data. Overall, there'll be fewer I/Os. Fewer I/Os means less CPU utilization. Good? So that's the theory. So what happens? You do that. So every night you increase the buffer size more and more and more. What happens? Every night you increase the buffer size from the previous night. You do fewer IOs. Number of IOs goes down, and CPU utilization goes down. So Ralph is getting happy. Well, that happens for the first 8 times. On the 9th time, you do the same thing. Yeah, give another few thousand bytes to buffers, I'll get even fewer IOs. Well, you got fewer IOs, but CPU utilization went up.
Because more CPU units working for the I/O.
Right, but if you have fewer IOs, why is CPU utilization going up? See, so far, for 8 days, I've increased the buffers. IOs, the number of IOs went down, and CPU utilization went down, number of computer cycles went down. Then all of a sudden, I did the same thing I did the last 8 days, increased the number of buffers, or the buffer size. But this time, the IOs went down, but CPU utilization went up. And that happened on the 9th and 10th day. And since you're supposed to write this report in 2 weeks, you better figure out something. Well, let's talk about what happens in I/O, what causes it, and why would you get this symptoms? Good? Okay, so we understand the problem now. So I'm going to go over this last overhead I did the last times, or sequence of.
Try to just scroll on when cursor is on the text.
What?
Видишь, полетел что-то интересное.
Okay. No.
No, just this guy, right?
Ми маємо трансляцію в YouTube?
Так. Там можливо будуть і затримки, які йшла мова, а трансляція є.
Okay, this is what I sent you today. Number 3. Life of an IO.
Є ніж. Щось таке завжди що не
Я потім поверну.
Зараз буде запис. Буде запис, правда?
Okay.
Буде запис, правда? Трансляція.
Так.
Так, ну.
I'll look at it. Yeah, I'll look at it.
Okay, good. What is this time?
Like you just try to record.
Just pause it.
Close it, yeah.
And that's all. Magic.
Okay.
Can you open it like full
Full screen?
Yeah.
It's down there.
Like 5. Yeah, wait.
Very good. Okay. So we're going to talk about this. Hopefully, from what we talked about here, you'll have enough knowledge to answer the question, or provide some thoughts of what's going on.
Like you had the one more slide from the previous lecture.
Yeah, and we'll go through this a little faster this time, and we'll spend a lot of time with those last 2 slides. Those last 2 slides contain the answer. It'll give you the knowledge to answer the question. There weren't too many people last time, so we're kind of redoing some of this. Don't do it at a different pace.
Okay.
Yeah. So, A lot of times when you think about computers and what they're doing things just like a human would do. So usually try to explain the way computers work with the way a human would do the same thing. Today's talk is about I/O and how the I/O system works. So what we're going to do is take a look at that from the standpoint of logistics. Same thing, instead of moving goods in a truck, you're going to move itty-bitty bits. They're going to be one place and you're going to copy them to someplace else. We'll have to talk about some other things in order to get this I/O. Virtual memory concepts, we talked about that before, but I'll just go over it quickly as a review. We'll compare that to personal computers I/O, or your PC works. We'll talk about buffers and paths. And we'll talk about interrupts. All those come into play in an I/O. So I/O is logistics. Instead of moving these containers around, you're moving these little tiny itty-bitty bits. The electrons are running up and down wires. Lights are going back and forth on fiber optics. You have to receive stuff, you got to deliver stuff. You're going to send the container off, put it on the truck, and off the truck goes. You have a routing system similar to a network, and it has to be received. In this case, we have a warehouse, and we have these receiving docks. Just like the trucking business, the bits work the same way. This receiving dock has to be available when the truck arrives. So this movement of the bits is similar to production nowadays, transportation logistics, that they call just-in-time. This dock is opened up for a 1 or 2 hour period. That's it. The truck has to show up in that time. Otherwise, what's being delivered isn't going to get delivered. The same thing with the computer. The bits are going to be sent, a whole path has to exist, and the receiver has to be ready to receive the bits. The path's not ready, the receiver's not ready, nothing gets delivered. Or it gets delayed. Well, we'll do it later. Logistics, you're thinking about the size of the truck. These are like the buffers we're talking about. How many itty-bitty bits are we going to move at a time? The size and weight, the cost of the equipment for this delivery. Unobstructed path, very important to keep this in mind. From the CPU to the disk has to be a continuous line that the bits can go on. Any break, there cannot be any delay. It's got to go all the way. That's called a channel path. We'll be talking about that. We're going to be thinking about how much time does it spend. The reason there's synchronous and asynchronous delivery of these itty-bitty bits. Synchronous means your program issues a read request, for example. What happens? Issues the read request to the access method, then the program stops. It's hanging around waiting for what? To receive the data. Once it receives the data, the program starts up again just where it left off. So that's called synchronous. A write operation is similar. The program's going to write a record, and it will not, it'll go into wait mode, sort of a suspend. It'll suspend until it gets information, a status back from the access method saying, I wrote it out, you can continue. If it doesn't get written out, then something has to happen in the meantime. Because that record could be your deposit in the bank. You go, oh, never mind, it's just a few dollars. So, the speed, the way this happens. A thing will keep recurring with large companies is something called service level objectives. Your whole life, I shouldn't say your whole life, very important in a large company is to meet your agreement. So IT makes agreement with the user. We're going to provide this, especially an online system. This is how much data we can handle, how many transactions per second. The response time will be a certain number of seconds, 1, 2, 3 seconds, 95% of the time, 99.99% of the time, the response time will be less than 5 seconds. So we have service level objectives. Cost is always a big deal. Keep in mind, you're using your PCs and you're not thinking like, I gotta pay for all this clicking that's going on. On the mainframe, they're spending on that system hundreds of thousands, typically millions of dollars per year. And that cost is being shared out amongst the users. So your user organization, like that personnel guy, he's paying for computer utilization. So that's why he's saying, look, do something to reduce cost. Make the program more efficient. We talked about it. If anybody has questions, say something. Well, we're going to talk about virtual storage. There's something called cache. Money is C-A-S-H,
Yeah.
like cash, dollars, okay, revenues. This cache is a storage. It's a storage where you're going to keep things. And what do we keep in computers? We keep data. So the idea is you have an I/O, you bring it in, cache is in main storage of the computer. I call it main memory. IBM, I notice, calls it main storage, so stick with it. So you have this data, you put it into main memory. If the computer needs it immediately, it uses it, but then maybe it needs the same data for another part of the task. Well, it's already in memory, it doesn't have to do another I/O. So caching is keeping data that you can either use again or have the high probability of using it again. IBM calls disks DASD. DASD comes in different types, but for IBM, DASD comes in a special format called key count data. Now that's going to be different than your PC or the Unix systems. Unix systems use fixed block. IBM mainframe uses key count data. Unix and your PC issue, the operating system that wants I/O to disk. It issues either an ATA command, or in the old days they used SCSI a lot, commands. IBM issues a channel program consisting of not ATA commands, but these CCWs, channel command words. And we'll see examples of this. We'll take a look at the hardware involved in moving records. So we're going to take two views today of this moving of data. We'll take a hardware view, which is good for background. But then we're going to take more of an operating system viewpoint of I/O. So we'll take a look at hardware that's involved in I/O. We'll take a look at the operating system viewpoint of an I/O. And then we have this example of a tuning, and we'll discuss that. questions? Somebody doesn't want to do any of this? We'll talk about virtual storage. I mentioned a little bit before. There's three things, objects involved in this. You have pages, frames, and slots. Pages are 4K blocks of virtual memory, virtual storage. Frames are 4K blocks of data in real memory. Real memory means like you can buy it, you can hold it, like it could go run across the street. Another object are slots. Slots are 4K blocks of data that are on what's called auxiliary storage, disk drive. We'll find out what page stealing is. We'll talk about swapping, they're sort of similar, and we'll talk about page fixing. Virtual storage, it says here that it's an illusion because it's mainly virtual storage is for programmers. It's to make life easy for programmers. A programmer, instead of worrying about, oh, I'm writing this program and it's too long, what do I do? Now, you can, with IBM systems, you can have a virtual address space of either 16 meg, 2 gigabytes, or, I forget, it's such a large, 64-bit address space, whatever that number that equals to. That's, that would be about 4 billion times 4 billion, whatever that number is. So you can have really big address space. Most programs will be using 31-bit addressing, which gives you an address space of 2 gigabytes. Now, where is this 2 gigabytes? It's in your head, virtual storage. And it gives you an address range. Each one of these is an address space. Each address space can be 2 gigabytes. Well, it's not all real storage. So what the computer is accessing will be in physical storage, like your DRAMs on your PC. The pages that are not being accessed can be paged out from physical memory to a disk drive. When they're needed again, at 4K, those 4K pieces are copied from auxiliary storage to real memory. All this moving around physically is handled by something called dynamic address translation. It's all hardware, it happens very rapidly. These particular disk drives, you usually select the very highest performance disk drive you have to work with virtual memory. There's tables kept by the operating system, by ZOS. Tables are kept to keep track of where all these virtual pages are. So set up your virtual memory. The pages can be either in real memory or auxiliary storage, disk drive. And there's tables set up to do that, to sort of keep the inventory of all that. There's 2 levels in this table. This shouldn't be too confusing, I hope. The Virtual storage is chopped up into 1 megabyte segments. Each 1 megabyte segment has a number of 256 4K pages. So a segment can have up to 256 entries. So it's just 2 levels of table. And the dynamic address translation, DAT, uses those tables to know where the data is, make sure what's in real memory is what the computer needs. When the computer needs something, the CPU needs data or an instruction, it's up to DAT, dynamic address translation, to make sure those pages are in real storage. Three definitions. A 4K block in real storage is called a frame. A 4K block of virtual storage is called a page. A 4K block in auxiliary storage, disk drive, is called a slot. Frames, pages, slots. Everybody okay out there on internet land? These people are all nodding their
There is
head.
only Roman.
Just Roman? Okay. Look, a major part of the operating system is to make sure that when the CPU needs data from main memory, it's going to be there. So there's a lot of scheduling that goes on, handling of the movement between auxiliary storage, real storage, and virtual storage. And there's 3 managers, pieces of software that do that. Auxiliary storage manager, real storage manager, virtual storage manager. That's all getting taken care of. Oh, page stealing, yes. Now, that sounds like bad pages, but it's not. What's going on is a program will access a part of virtual storage, and that part of virtual storage is in a 4K page, but it's not in real memory, it's on auxiliary storage. What'll happen is it'll take that 4K bytes from DASD, the disk drive, and move it into real memory. If all the real memory is already used, what will happen? One of those pages, one of those frames in real memory will get stolen, get thrown out, or moved over to auxiliary storage. And then that data that's needed, it's on auxiliary storage, will move in, so it's sort of sludge. Sometimes, if a program, let's say the program's waiting for I/O. I/O, we talked about last time. I/O, we'll reverse it. The CPU is running, let's say, one thing every second. I/O takes a year. So that's the order of magnitudes difference between the speed of the CPU and the speed of disk access. So let's say you have a program, your program issued an I/O, and what's it going to do? Sit around for a year. In the meantime, the CPU says, hey, take all this stuff to do with that program, swap it into the disk drive. When I find out that the I/O finished, I'll start up this program again. I'll start it up by taking it from auxiliary storage to disk drive and moving all those pages into real memory, real storage. So we have page stealing. When you take the whole task, that's called swapping. I have a big picture. The program wants to write to the computer's memory. Main storage. The program is going to write to a buffer in memory. The audio system is going to do what? Take it from that real memory and move it out to disk. That's a write, reads the opposite. Just take a look. This is what happens in your PC. So it has a similar architecture that we're talking about. Some things are different. Your PC has something called a north bridge and south bridge. These are only called north and south because when you look at them, north is up in Western maps. So the north bridge is connected to the CPU, and it's also connected to this DRAM. So it's very fast, it handles a lot. It's also connected to your video card. So this is very, very fast. Now a little slower. Where's my, hooked up to the PCI will be the disk drives. A little slower, so the north bridge talks to the south bridge, another piece of chip, so to speak. And then that chip talks to the PCI bus, that talks to, communicates with the disk drives in your machine. Oh, I forgot that. FSB is front side bus. Let me just back up this last thing. These used to be different chips. Nowadays, they've started combining, Intel combines sometimes all of them in one chip. But the architecture still looks like this. If you have like little electronic eyeballs, you can see that. Okay, this similar thing, CPU on top, north bridge. On the right are your main memory, DRAM, for example, graphics card. It's a very high-speed bus. Every time the CPU does something, it's getting what to do from main memory, main storage. If it's doing I/O, IDE or SATA, Ethernet, so forth, it's going to go then through the south bridge, which will handle the protocols to the disk drive. So the serial ATA is going to be issuing. Serial ATA are two things. One, it's the specifications for how the wires look. You hook them up in your computer, there's like this SATA wires. But also, on that wire are ATA commands. Commands like format the disk. What is the status of the disk? Read something. Where to read, what to read, so forth. So those are the commands coming out of ATA. Last part, buffers. This is both in datacom and every place in the computer world. There's a differences of speed constantly. The internet, your data communications is running at a much slower speed than your CPU. Your disk drive is running faster than your datacom, slower than your CPU. So every time you have a difference in speeds, it has to be accommodated. That difference has to be taken care of by a buffer. So buffer allows things to go in fast, go out slow. I also can kind of turn this around and slow to fast. So there's a difference in speed. I have this only to show that you have to have a constant connection between the two ends of a path. Here's our buffering. One way to get a drink of water. Another way to get a drink of water is two levels of buffering. Put the water in a big container. The container pours it out in the glass, and you can handle drinking from a glass. So, what we have here, this is one of the interesting things I found when I arrived here in Ukraine. You have to have a constant path to get the data. Now, there's something in the system called interrupts. So what's going on is the CPU is kind of merrily going along, and then all of a sudden something happens. Sometimes what happens is not good. You're losing power. Or somebody tries to divide by 0. And the computer just goes, I don't know what to do. So when these events happen, they create interrupts that tells the computer to stop what you're doing, save what you're doing, and start on this other routine. The other routine, in the examples I have, like start shutting down because you lost power. Divide by 0, kind of just clean that up, finish that task, just end it, and go on with some other task. Do somebody's program that doesn't divide by 0. So those are called interrupts. What's getting interrupted, very clearly now, what's getting interrupted is the CPU. And every time it gets an interrupt, it stops what it's doing, saves its state, and starts working on some other program. So, one of the interrupts we get that we're concerned about here is I/O interrupt. So what happens is a read request is issued. The CPU does what? Off on some other job. A year later, that whole disk drive system comes back and saying, well, finally I got the information. And this interrupt, the I/O interrupt, is sort of like ringing the doorbell. Ding, ding. CPU opens the door, says, oh, come on in. We start up your program that's actually going to use this information. We have just the relative length of time to do things, 1 year and 1 second. The computer's running like something once every second. The I/O would be like once a year. We have this hardware. Is everybody doing okay? Roman? Roman is he okay?
He leave us.
Oh, okay. Here's the hardware view. Usually our concern is more of the operating system view. We're doing this just enough to give you an idea of what's happening with hardware and to relate it with what the operating system is worried about. So, operating system view. Up on top are partitions. These partitions are called in IBM L parts, logical partitions. They're sort of a hardware virtual machine. Controlling all these partitions, like spreading out the work, is the hypervisor, VM. HSA, first compared to your PC. On your PC, you have plug and play. You get a memory stick, you plug it in, it goes, oh, Jim just put in a memory stick. I'll add that to my list of hardware. Well, the mainframe doesn't work that way. Somebody getting the big bucks has to tell the mainframe, here's what's connected. And the mainframe keeps that information in the hardware systems area. So HSA is not available to programs. It's usually the customer engineer, the guy from IBM. He comes in and he does this. So all these disk drives, everything connected, that information is HSA. There's memory. Memory, there's about 3 or 4 levels of cache with the mainframe between the CPU and like the I/O. So here that's just represented by 1 bar saying cache. So what happens is, let's take a look at this. I'll start at the bottom. Nowadays, the disk drives and the disk drive controllers are connected with fiber optics. There's 2 major protocols used in mainframes, SCON and FICON. The latest one is SCON. I'm sorry, I did that backwards. SCON, FICON is the newer one. This thing is running, I think it's running now, it was 400 gigabytes per second. It's around 800 gigabytes. Lots of little light going back and forth. Connected to this is the logical channel subsystem. Logical channel subsystem. Memory, MBA stands for memory bus adapter. And notice it's connected to what? The channel, and it's connected to cache. So the goal of the bus adapter is to transfer data from cache out to the channel, which will then go to the disk drive, or from the disk drive, deposited that amount of data in cache. There's a processor, sort of an extra processor, and what this guy does, this guy's doing the movement of the data back and forth between cache and these lines. This guy is determining, for one thing, the path. Because, for example, this guy can send it like through here. There's lots of paths. And it also, the path to write the data or request the data may be different than the path that the data follows to get back. So it could be, so this guy's job is kind of complicated because he has to make sure what's available. Let's set up a path, and when it responds, the data response, which includes the data and the status code, has to end up back here and into cache at the right place. Oh, I had a question last time. Each one of these PUs stands for processing unit. And you could look at those on the PC, you got cores. So you could look at these sort of like cores. Each one of these are individual processors. The hypervisor in this case, this partition says, I'm ready to do some work. The hypervisor will assign one of these processors to that partition to accomplish that particular task. When the processor gets done, the hypervisor notes that, will give the processor to some other task from one of the other partitions, or maybe even the same partition. These processor units they have different functions. Some of them just use regular central processor, CPU. Some of them are SAPs, the System Assistant Processor. These help out the I/O code execution. Some of these processors are specialized for very efficiently handling database code or Java code, taking care of byte code. Good question.
Yeah.
This thing gets complicated, and IBM over the years has simplified or made a reduced waiting time.
It's okay.
Hmm?
Everything's okay.
You sure?
Yep.
Okay. So, it used to be a channel had to be set up for a path completely to one disk, and the disk, when it responded with the information, had to use the same channel. Now, the request and the response can go over different paths. If there's more paths available, it's like you walking home. If one road is blocked, you can take another path. Or if one road's slow, more likely.
Wait, it's a way to read and write to the one disk at the same time?
Yes. Keep in mind what it's, an I/O, one is going to be the request. The channel program is going to go from the mainframe, end up on the disk. The disk is going to respond with the data, and they can nowadays be on different paths. To answer your question. Yes?
Yeah.
Okay. We've talked about this. The best I/O is
No I/O.
no I/O. You'd be surprised the number of programs that are reading a record, doing a bunch of things. Later on, they need the same information, they're doing another I/O. So you look for those opportunities when you're tuning systems or reducing I/O. Do you really need the I/O? Or because you got it earlier and just kept it? One of the things with, this is another question I have for tomorrow, or not tomorrow, next class. One of the things we have is something called locality of reference. This is especially useful during sequential processing. Sequential processing, this would be our backup situation. What are we doing? You just start at the beginning of the database or the file, read, write, read the next one, write the next one. It's sequential processing. So if you're doing sequential processing, very likely, of course, sequential. Whatever record you're reading, it's very likely you're going to need the next several records. So the idea is not only to get the current record, but get the next ones in line. So that reduces I/O. So that's your locality of reference. A lot of times, even in direct access systems, you're processing the data and you end up with a lot of, for example, you're processing the data for a particular office, the New York office. If you get one person from the New York office, it's very likely the other guys in that office, if the records are close physically, getting all those together will speed up processing. So that's a random or direct processing. And the idea is you can utilize locality of reference. But this also has to do, this works by putting stuff in cache if you use it. If you bring in a lot of records, and the probability of using another one of the nearby records is very low, then you just wasted a lot of movement of data. Does everybody follow that part? just change a little bit, we're gonna get into hardware, and I just want to talk about count key data, formatting of the disk, and what a disk looks like. This is very quickly. There's a disk platter revolving around. It's usually made of some ceramic material with a very low temperature coefficient of expansion. It's spinning around. On the average, this guy has to have a half a turn before you start at the required record that you're looking for. So one delay is rotational delay. So these disk drives, they try to make them spin around faster and faster and faster and faster. And now I think they're around 20K revolutions per minute. I think your PCs probably have like 5,000, 7,200, something like that, revolutions per minute. Each platter, the top and the bottom, is covered with magnetic material, and it can be read by these read-write heads. The read-write heads, the assembly moves in very small increments. Each one of those increments describes a track on the disk drive. This guy's okay with this one?
Yeah.
Good, okay. Important is when you shut this guy off, these disk read-write heads just don't flop down and rust on the surface. Instead, this whole assembly moves over to an unload ramp. So if you're carrying around the disk or moving around your PC, it's not destroying the disk by the read-write head hitting the surface. They keep improving the recording density on these. It's called areal density, the technical term. They're doing things, sometimes they're really close. The magnets first were like all lying down, and now they're up and down. So you can put more people like in the room, if they're standing up, or put more little itty-bitty magnets on the surface if they're vertical aligned. Track, in PC land, you call these sectors, cylinders, tracks. So you got track, cylinders, records. But IBM's different. So IBM, here's a track, it's circular, and we spread it out linearly. And it starts off with like a little index point, little hardware area, so the disk drive knows, okay, this is the start of the track. And then it has records. Each record has 3 parts, or at least 2 parts. Each record has a count key data. They all have a count field. They may or may not have a key field, and they all have a data field. The count field has the length of the data field. So when the I/O subsystem, when it issues a series of channel commands, it's going to, if it's a read, it's going to say what? Go to this cylinder, this track, and get this record. So here's an example of a channel program. They're very small. The first command word, CCW, channel command words, in this case, is going to say seek. Along with the seek will be a cylinder number and a head number. This seek is a 6-byte instruction. Next instruction is a search. So it's on a cylinder, on the correct track, and it's looking for a specific record, trying to get a match on the key. So it's doing a search, key equals the key value. 3. If the first record is not 3, record number 3, what's going to happen? It's going to hit this instruction called a TIC, transfer in channel. Everybody else would call this a go-to. Where's it going to go? -8. 6 bytes, 2 bytes. So what this is going to do is, if it doesn't equal, this is going to go back to the seek. So it's going to keep looking at each record until it gets to the end of the track. If it's not there, then it comes out and says, record not found, and reports that back to the I/O system. If it does, it's then going to do what? Take this data and put it into this particular buffer.
Oh, yes.
Finally.
Finally.
Okay.
I will call Roman. 1 second.
Oh, Roman wanted to wait for this thing. I'm going to switch from this to, because these next 2 slides, I have notes underneath them. So you may want to go to the, can I do this?
I will go through. Easy enough.
What I'd like is the view of the, can you change, I can't, it's in Ukrainian. Could you change this to read notes, the notes?
Нотатки отам бачиш. Внизу.
Like view notes in English.
User program. А ну тикни ще раз, будь. User program connects.
Ah, good. Oh, let's see, what can we do? It's not too big. You guys can look at these on your,
Like, we can open this presentation on our computers, like,
Yeah.
have it in Slack.
and look it on it in
Yeah.
note format, good. Good. Oh, thank you. This is the operating system viewpoint of an I/O. So the I/O is going to start out, you see these guys are numbered from 1 through A. I'm a computer, 1, 2, 3, 4, 5, 6, 7, 8, 9, what's next?
A.
Because I'm in hex. See, we programmers, we talk in hex. Humans talk from 0 to 9. Computer people talk from 0 through F. Okay, so the first thing, number 1, is the user program is going to somewhere along the line issue an open. You guys had a program, Pascal, Python?
Mm-hmm.
Okay, so you know what an open is. Yeah, open, read, write, close, correct? Okay, so it's simple. You're going to do an open macro. What's a macro? Does that sound familiar to you guys?
No.
Okay, macro is an assembly program. A macro is an assembly statement that is going to expand into a number of individual.
Nice.
Okay. It's sort of like, it acts like an include in an assembly program. So the open macro, you're just going to say open, but inside it's going to expand into all kinds of, create a structure, fill in information about the file, the data set. So you'll issue an open macro. Somewhere along the line, it's going to do a get, a put, or erase, or some kind of verb, whatever your program language has. Read, write, delete, something. What's going to happen? That particular get is a call to the access method. Now, push this up. And so here's your address space. You're doing a call to the access method. The access method is going to do what? It's going to start creating it will create the channel program. In addition, it's going to set aside these buffers, so when the data comes in, so we're doing a read. So when the data comes in, there's going to be a buffer for that data to go into. It has to remember where that buffer is. Make sense? Because when the data comes back, that buffer has to be in the same place. It doesn't have to, but almost all programs, especially when you start writing, will be synchronous. What does that mean? When your program issues the read statement, the program's going to stop. And it's going to wait till it gets the data, then it'll continue on. So it's synchronous. It's in synchronous with the access, the getting the data. The access method is also responsible for, hey, I can't find the data. You asked for a record, I don't have a record. I may not have the file. So, if it's something like a hardware failure, it may try to redrive, usually about 3 times. They'll try and issue the I/O again. Hey, try it again, try it again. Then after a couple, 3 times, it goes, this drive's bad, I'm not going to get the data. Now, so the access method sets up the channel program, and then it does a execute channel program instruction. That execute channel program instruction is a call to the I/O driver. Now, these I/O drivers, there are several of them here, so let me just mention those. We'll talk about them later. So here, just kind of consider all file systems are the same, but they're really not. There's a number of file systems, just like Unix has. File systems, MM, are VSAM file systems. There's actually 4 types, and we'll be talking about all these, and you'll be able to use them. JES stands for Job Entry System. It's actually how the system that takes your job saying, hey, could you run this program? And when it gets done running the program, it gives the output to you, either on a terminal or a piece of paper or someplace. So the output, and it's sort of like sys in, sys out in Linux. So it issues the, what else do I have here? Oh, just to mention, VTAM is the software to handle data communications in the mainframe. So this execute channel program also works with data communication in a similar fashion. We're not talking about datacom in this time. So in this case, let's issue a channel program. The channel program calls the I/O driver. Now the I/O driver is going to issue a supervisory call. that sounds like a big deal, right? So here's what's going on. You're running in problem state. So this is your address space. A supervisory call is going to be a call to another address space. Now that address space actually can do things to the disks. Your program cannot directly access disks. That's different than you usually have with Linux or certainly Windows.
Supervisor, and then supervisor has access to the disk.
Exactly. And the supervisor is like ring 0, if you want to look at it that way. It's handling under, it's like under root. Now, keep in mind, this system doesn't have a root password like you have in Unix. It has security, but it's in a different way. But there's no overall, if you've got root, you can write every place. You can't do that because you're the personnel person working on the personnel system, and you decide, well, I'll just reboot. There goes 20,000 users. So, what are you doing? You issue the EXCP, supervisory call, the IO driver goes into the memory address where that those routines are stored. Oh. What's number 4? You guys have that?
I look now.
Probably scroll down.
I'm turning the window down with this. I have more notes. On this
Like
one,
this
pardon?
mouse wheel, you can scroll down probably. No, this text. Oh.
No, that was not right.
Thank you, appreciate it.
Visualization. This one, this one. Okay, I'll do this one.
Oh, I shut it off.
Yes.
Stupid me, thank you.
And
Yeah. And then a note.
yeah.
Okay, if there are no binding.
Okay.
That's okay.
So here's where we left off. So I'll just kind of use this. Oh,
I can make it smaller if you want.
oh, this is good.
Okay.
So first over here, what happened? We're in the supervisor address space. And an important thing is that buffer cannot go away. Because when the information that we're trying to read comes back, it has to find that buffer, and that buffer physically is where? Virtual store? No. Real storage.
RAM?
Make sense? Because the CPU doesn't know about
This.
virtual storage, it's in your head. It's only in real storage. So what's going to happen is, it's going to page fix. Fixing a page or a page fix, that says this page, this 4K, cannot be taken out of real storage and put into auxiliary storage. Make sense?
Yeah.
Do you see why? You look like a non-believer.
No. It's okay.
Good? You can explain this to someone?
Of course.
Okay.
We
So-
talked about it last time.
Because if it gets paged, then it's, the hardware doesn't know where to deposit the stuff. So you do a page fix, this is going to be important pretty soon. It's a hint.
I I think I know the answer for the question.
Ah, good, good, good. Now, if there's no pending operations for the device we're talking about is the disk device. How many IOs can you have to a physical disk at one time?
255?
One.
Oh, no, it's just another number.
It's okay.
A lot of, we are programmers, so there are a lot of problems.
256, something like that. Yes. Do you guys see why? You can only have one IO to one physical drive at a time. So it's going to make sure that that device is not busy. If it's not busy, then it's going to connect that whole path from the channel subsystem all the way to the drive, the controller of the drive, and that request goes out to the drive. The drive gets the data, let me see. That particular path is done by that SAP chip that we saw in the hardware, overview. The disk drive gets the data. It keeps it in the disk drive's buffer. When it's all set, that SAP guy again determines a path. The data comes all the way back from the disk drive's buffer through the fiber channel up into cache. And that part of cache is in that same fixed page or pages in real storage. Let me try this again. Next slide. So when it comes back, the I/O subsystem is going to interrupt the CPU. And it's going to say, hey, I'm all done. The CPU is going to create a task control block, put it on the queue of things to be done. Where on the queue, depending on the priority of your program. Eventually it's going to get picked up. The data is now available to your program.
Okay, and if we have a buffer which is bigger than RAM,
Bigger than what?
RAM, real storage,
Uh,
we need to access one more time the SD to get the additional information.
okay. If it does a get main, which means let's say get main storage, that storage has to exist. If it doesn't exist, then the get main doesn't work.
Like if
But you're close.
If there is not enough memory in RAM, it can't translate files.
That's not the problem in that quiz.
No, okay. I'm just thinking.
But that's good. I want you to be thinking. Well, what are you going to do about Roger's system?
Okay, and if we have these fixed pages with information about data, about storage, and there is not enough storage to put data.
Okay, it's not a lack of storage. Okay, here's what's going on. I'll give you more hints. Where are these buffers?
No,
Okay, so here,
virtual memory. Oh.
wait, we went through this whole I/O thing, and where did the data end up? It has to be in real memory, because you fixed those guys, remember?
Yes.
Yeah.
But buffer is bigger than real memory.
No, you just get more, you get as many pages as the buffer is. So what you've been doing all week for this past 8 days, you keep saying to your program, I want a bigger buffer, I want a bigger buffer, I want a bigger buffer. So the buffer's kind of getting bigger and bigger and bigger.
But buffer is stored in real memory.
Eventually it's got to be in real memory because that's what's getting fixed.
So our buffer can be, the size of buffer can be bigger than the size of our real memory.
No, it can't be bigger than real memory, but keep in mind in the system you have, like you can put a terabyte of real memory.
Okay.
Okay, so the system, so here's one answer, I mean, not an answer, but the situation. You are getting that buffer size you're asking for. You keep asking for bigger and bigger, but it's there and you're getting it. So what happened? More and more data is coming in, and it's going into real storage. And then what happens to it? This is a
And
copy
then
operation,
the-
it's taking a record copy.
CPU tries to handle this data.
I'm sorry.
CPU tries to handle this data, but
Yeah.
the amount of this data is bigger,
Mhm.
so it's like more pressure on the CPU.
It's hanging around the memory too long.
Like it's when the CPU is like working on some part of the data,
Yeah,
another part is still in the real memory.
right. And if some stays in real memory too long, what happens?
Like it goes back to the DSD.
It goes to disk, it gets paged out.
Yeah.
Good? Okay, that paging out is, now, that's increasing CPU utilization. You don't see the IOs. The system sees all that work. Is it making sense?
And if we will change the algorithm which handling the like which part of the data can be erased or
Yeah.
swapped to the DSD.
So actually what you did in this for Roger, you did the correct thing. You keep increasing the buffer little by little. And then you'll notice IOs keep going down because every time you're moving it, you're moving more and more data. So total data divided by size of an IO, size of IO is bigger, the total IOs are less. So that's a good thing. But then you're watching for CPU utilization, it's going down, 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 now it starts increasing. What do? Back off, and that's the correct buffer.
Bet and play.
Hmm?
Bet and play.
Is this clear?
Yeah, that makes sense.
So on your first job, you'll be able to do this?
Of course.
Okay.
If they will pay us, they will do it.
The idea, whether they pay you or not, the idea is you're gonna do good work. Okay? It's not like you're not paying me enough, I'm doing bad work today.
I think it's about me.
Yeah, if you say that in an interview, I'm not sure you're gonna get hired. Your goal is to do good work, you want a happy Roger. That's your goal in life, making all the Rogers happy at your installation.
Hello?
Okay.
Well, okay, yeah.
So the reason I'm trying to do a lot with the I/O is it's likely the first thing you're going to get involved with from a system standpoint at your job. You're probably not, I'm not going to say probably, you won't. Nobody's going to let you handle the workload manager. You just need experience, you need to understand the politics, the priorities of all these jobs before you handle something like that. But I/O usually you get a chance to play around. You get a chance to play with the buffering. You look at, it's not unlikely that somebody will say, here's your, let me start over. A big shop, the first thing you're going to do probably is maintain a current system. You're going to work for a bank. They've been doing banking for 10, 20, 50, maybe even more years. So you're not going to go in and write a new banking program.
Yeah, and your task is to maintain this old system, but not try to...
It's not old, it's running now, it's new. They might have maintained it last month.
To improve.
Yeah, they're gonna ask you, they're gonna come up, typical, what happens, that companies keep coming up with products. I got it. Let's say you work for a casino. Like Wynn's Casino in Las Vegas. Sound like a good job?
not
Okay.
bad.
So you work in this casino and you're working on a set of programs, customer relation programs. So at a casino, the big thing they got is whales. What's a whale? Oh, you guys aren't into casino business, sorry.
Those people who win every time?
People who spend a lot of money,
Or
okay? So whales are like some guy from China with more money than, so they come in and they just bet a lot of money. So you're not worried about them winning, you're worried about them betting lots of money. Because the odds, a little bit of the odds are for the house, the casino. I'm at Catholic University talking about this.
It's okay.
Okay. But you get the idea. So they have a program that they want to treat whales very nicely. So typically what you're going to be doing is they'll have a new product. I should get back to banking.
No,
No.
Okay.
no, it's good.
Oh, okay. I thought most people understand. Gambling, not that you should gamble, but other people do. And this is how you make money from gamblers. If you can get them gambling a lot, and what you want your casino to be doing is attracting these whales. So your casino says, look, we got these little whales, and then we'd like a program for mini whales. Start attracting, people aren't filthy rich, but they're not oligarchs, but they're like pretty well off. We want to try attracting them, and we're going to give these people, we're going to identify these gamblers, and we're going to assign each one of them to a salesperson. So now you have to implement this. Whatever they do in a business, it has to be reflected in the systems, computer systems. So they're going to ask you, first you have to analyze, like, what do we have to watch? We have to associate a salesperson to this set of customers, and then that salesperson is going to get measured somehow. We're going to measure the cost of the mini whale. Like maybe we'll give them a small suite and we'll give them free drinks. Yeah, so you want to measure the cost of acquiring a whale, attracting and keeping the whale, with the amount of money this guy's betting.
Or find the sneaky players.
And find what?
Sneaky players, which like play. Like you know, when some games in casino can be played in a bad way.
You've been watching too many movies. No, the casinos are not they're gonna lose business if they look like they're cheating. They got a certain, all they want is people coming in and betting.
Yeah.
And it's a statistical, it's mathematics that they'll make money. If they cheat, they'll lose customers.
But
No, I'm talking about when customers cheat, there are special systems to find people.
Yeah, it's pretty hard to cheat in casinos.
We had an idea to try, but
have you watched the
Good
movie
luck.
named 21?
Pardon?
Have you watched the movie named 21?
No, but I know the game, blackjack.
Yes.
You got blackjack, baccarat.
Yeah, there was a movie about a man, a mathematician who.
Ah, with the college kids.
Yeah.
Yes, he
From
cheated,
MIT.
Yes.
yeah.
He just knew how to count cards and something like this.
Yeah, he had a card counting system and he moved people around. And he got caught. They went to jail. See what I mean? It's like, yeah, this is Catholic University. I don't care if you work for a casino, but don't cheat. It's just, you'll make enough money. So the idea is what you're going to be doing, and this is actually a good, what you'll be doing is maintenance, most likely. Maintenance is sometimes fixing a problem. All of a sudden, it's a weird transaction comes through, and it's just the particular program stops. They just didn't anticipate this sequence of data coming in. So put a patch in and fix that. most frequently, they'll have another product or function, and you'll write a routine, and you have to fit it into the current system. So what you'll be doing a lot of is a couple things. One is, you're gonna be trying to understand just what does this program do? What are the inputs, what are the outputs, kind of processes going on in between, and you'll have to understand a little bit about the business. If you're working at a casino, you're gonna learn what a whale is, that kind of thing, you follow?
And
Or if you're at a bank, you're
for
gonna,
example, okay, what to do when there is some situation, when some new functions of these programs, for example, are so hard to do that you need to rewrite the whole system for them.
or you're gonna attach it to the current system. Usually they've already doing something similar. You follow? If you go to a bank, they're not gonna do banking in a totally different way. They'll add a product. So what would be a product at a bank? You go to the bank and all of a sudden they decide it would be good if we assigned large depositors a representative in the bank that would periodically call and say, how's it going? And try to encourage sales of the bank, other bank products. So if that happens, you're gonna have to expand your computer system to do what? Match, it has to keep track of what? The representatives and the customers that are in this group. You're gonna have to measure the success, the metrics for how well this is going for the individual salesperson and for the bank as a whole. So you're gonna be adding probably little data elements maybe, making another little table. You know, it's that kind of system, it's hierarchical. You'll be adding some more branches.
But we need still knowledge for this.
Well, one of the things you're gonna do when you work for a company, you're gonna read a couple of books like, what do they do? If you work for a bank, I would suggest getting a book and reading banking.
Get the whole.
You don't go in like, hey, this is a neat place, a nice office, what do you do here anyway? You know, like you come into university, like an admin staff, you're gonna find out like, how does the enrollment system work? Right, you're not gonna say, well, like, oh, the university, this is neat. What do you do here? Well, we teach people, we gotta enroll them, we gotta collect money. We have endowments, we have to encourage endowments. Lots of accounting. So one of the things you're gonna do when you get out there, what I suggest you do is read up on the company. First, when you interview, I always read a book on the company or their business. I didn't go in like, you know, how does this work? I typically did the same thing you do at the start of when you hack into a company. The first thing you're gonna do is reconnoiter. So you're gonna like Google stock the company. You're gonna find out, you're gonna go to, like monster.com, do they use that here? It's like a job system.
No.
Okay, so you're gonna go to that and look, like who have they been hiring? What are the skills they've been looking for? It tells you, like when you go there, if a relational database, start talking relational database. If you don't remember from school, maybe read a book. You know, so you prepare for the interview that I have the skills you need. You already know what skills they need. You don't go like I said, you don't go to a bank saying, what do you do here anyway? I like this chair. So your first thing is probably going to be maintenance. The other thing about maintenance is like language. When you learn the language, Ukrainian, what did the teachers have you do? Read a lot. Is that correct?
Yes.
I know in English, they take English literature, they don't expect me to become a poet or to write like Gone with the Wind. But the idea is by reading these books, I have an idea of what good language is, how to express yourself. So one of the advantages of maintenance programming is usually you get to read some decent code, sometimes really bad code. But a lot of times you see some interesting ways they did it, how did they approach this, and you just learn, like somebody else, they probably not there anymore, or could be, but very likely not. But by looking at their code, you see their approach to a system and how they designed it. So that's my pitch on this. So maintenance is a lot of fun. Of course, what I was going to do, I forgot what it was. It's good. Is it good? Good session?
Yeah.
Yeah, thanks.
What are we going to do next time? Oh, how are you guys reading that book?
That book, no,
Yeah.
A little bit, and we are just doing exercises on.
you are giving a lot of information which is associated with the book, so.
Oh, it's kind of fitting?
Yeah, okay, so it's like better to read the lectures.
Okay. I'm trying to, next time, I'm trying to start fitting into actually working on this machine. Okay, this is the first time I've had a computer course ever where I didn't start off right away, start doing something on, start typing, so to speak. So I'll try and do something there. And I suggested to Dr. Oleg to maybe assembler would be good.
Assembler?
Yeah.
Oh, yes. I was waiting for it, like.
Yeah. The chance of you getting a job in assembler
Are 0?
on a mainframe is very low. But the knowledge of assembler will help your entire career. So it's one of the things you can learn it later. If you learned it now, it'll help your whole career. Understanding what the machine's doing.
And in business analysis career?
No.
Well, you're doing business analysis, but I presume you'll be talking about business systems.
Like every language is translated to assembler and then to machine code.
Yeah. And if you're doing business systems, it's just computers nowadays are in all companies. Your chance of working on a farm on their manual paper system, I don't think is your aspiration, is it? No. Yeah. So this will help you understand how the computer works, things like that. Have faith. Thank you, guys.
Thanks.
Thanks.
Can somebody tell me, I'd like to find out how to use the, last time I've been walking, it takes a long time, but I need to go to a Mashuka that goes toward my house,
And where is your house?
Tajikska.
Tajikska. I have no idea where.
Okay, I'll show you on here. You guys have time? Just
Yeah, but I'm not coming with our transport, so.
okay, here. I'll show you one. I don't know.
It's near Kukulanka.
It's by the cemetery.
Okay, we will just go.
Yes.
Oh, okay. Маршрутка.
Probably have.
На пасічну, коротше, треба.
Я так розбираюся на нашій вулиці, що
Я не маю поняття, де пасічна.
я не маю поняття. Забувай консерватора не може.
Ну, тільки непогано. Ого.
Що, я розумію, що ти таджицька і домашня.
І що?
Таджицька вік.
Look at you tonight.
А окей, я не пам'ятаю.
You found it?
Ні. Ого.
I could ask my dad.
What address is it?
Таджицька.
And
Oh, yeah.
It's not a very big street, you know.
I don't know.
I'll show you here. Where is that guy?
питання. Як доїхати від УКУ? Ти знаєш, як доїхати від УКУ на таджицьку? Таджицька то біля Пес. Зараз чуєш? Добре. Давай.
Should I answer between?
You can take 27 bus.
Oh, here it is.
Oh, we Dalek, the best.
Yeah, near Oku and just to the Tajitska street.
Ah, yes.
So here is Oku, our building.
Yeah.
And do you know where is bus stop? Just behind the collegium.
Maybe you guys can just,
Yeah.
Okay.
it's not too much.
Yeah.
If it is, yeah.
And then you can sit on the 27th bus,
Yeah,
and it will go just
it goes close enough from also.
close enough to Tajitska
Yeah, I
street.
think you will.
Here is a bus
It's
stop.
пасічна є.
Oh, I know, yeah, okay,
You will recognize your street.
yeah, super.
Yeah.
It's 27?
Yes.
I look when it comes.
Oh, okay.
I'm just in time, yeah.
Yes.
It's going like every 12 minutes or
Oh,
something like that.
good, okay. So, we were talking, and what's the answer? Who's gonna, well, doctor, who's gonna describe the problem and the answer to Dr.
Конечно же, я.
To the doctor?
Ну, давай.
Ну, там, коли береться, була проблема, що треба було якось зменшити нагрузку на I/O операції, і програміст вирішив збільшувати буфер.
Так, то я ще був.
А буфер зберігається в RAM, але ж є віртуальна пам'ять, як працює. Там, якщо ми беремо великий бафер, і там багато даних є, де багато файлів. Якщо ми не працюємо над деяким, ну, процесор працює над якоюсь певною кількістю файлів. А інші файли стоять типу АФК. Одні файли, а коли вони стоять, то вони ж свапуються в DSD, і через то вони видаляються, і потім треба знову прогружати. І через це
Я так був подумав, думаю, мало може. Ще якісь нюанси, я не знаю. До чого ви домовилися, коли наступний раз?
Ми зараз не розуміємо.
А не домовлялися, чи ви не змогли домовитися?
Ні, не домовлялися.
Good. So, then we would meet next time.
Wednesday.
Wednesday?
Then, same time.
Yeah.
That's good.
В наші є питання, чи будуть викладали якісь там курси, щось таке між 3 і 7 числом. Бо нам прийшла можливість піти на курс один.
Ні, не буде.
Не буде.
То, що щось десь, помилка на інтерфейсах, нічого не буде, тобто 14-го, там, коли почнеться навчання, 14-го починається.
Ну, здається, 17.
Ну, 14.
14
Десь
це
так,
п'ятниця.
десь так.
І там здається.
Ні, ну тобто перед тим не буде нічого. Це ціла купа дрібних непорозумінь, коли прийшло до практики, вирішили, що це стих за
А Five Pro? Five Pro?
ясно. Нічого. Jim, I need to stop translation.
Oh, yeah. Oh, it's okay if you talk to Brandon. It doesn't bother me. You can talk about me. I don't feel bad.
We are talking about it pro.
Oh, yes, I know.
Знаєте, є справді, є робота для вас, якщо б ви погодилися, у нас є ці їх треба відтестувати на чутливість. Тобто я зараз це потрошки роблю, це доволі марудна робота, тобто вона вимагає акуратності, це одній людині забирає дні. І якщо ви на це готові, тобто це що? Я вам даю 3 чутливих прилади. Ви тобто, щось робите, час від часу міряєте, співставляєте і просто записуєте. То воно показало то, ті там показали таке. Якщо ви згодні, то я з задоволенням вас покличу. Кажіть коли. Ну, коли ви можете, маєте настрій. Коли забагато. Знаєте, в середу закінчимо, йдемо туди. Це я зі стейта взяв тут, якщо вам є кращі ідеї, вони підходять, то ви кажіть.
Ну, я точно не зможу.
Краще в четвер.
Давайте в четвер.
Не пізніше.
Який час?
Ні. Насправді в середу було б прикольно зразу після того.
подумайте насправді. Тобто мені вже цього
Тільки 2 години у світі?
Ну все одно. Скільки будемо, стільки будемо.
Ти знаєш, що від 2 рази в місто їздити сложно підряд. Мені тут не очі.
На крайній випадок можемо окремо піти, там, бо я якісь моя з художником маю зустріч, я там все маю задачі, тобто можемо піти з вами, там чи хто зможе в середу, потім ще в четвер.
Давайте вже в середу ми з...
Все просто.
Ну, тоді ж попередньо в середу. Добре. Наразі дякую. Побачення.
Бай.
Bye, thanks a lot.
Okay, thank you.
We will show you.
Oh, thank you. Yeah, so we're good. Okay. You're gonna show me how to get to the Bashuka now. Okay. And I'll write you, if we can get online, that'd be good. I'll start, I'll anticipate we can.
That's it. I will start the translation and then we will go.
Okay.
I will check. Students send me what model I should take to see those.
Oh, okay.
Then,
Yeah.
I'll check it and show you, and we can use it. I hope.
Okay, good.
Oh.
It'll be fun, good. Okay, I'll see you later.
No, Jim, I'll show you. Just a second. I will tell you.